Hi, I'm Sam from the Plasma Test Stand team. What you just saw was the Busek BHT 200 thruster, a plasma engine that we use for our testing. Plasma engines like the BHT can be quite useful in deep space travel due to the low mass of propellant needed. However, they are very difficult to characterize on Earth. Our sponsor, Dr. Badashev, researches these engines here at Northeastern. For our project, we designed a system to measure thrust from plasma thrusters.
Hull thrusters use an annular geometry to create a cylindrical flow path for the inert gas, ions, and electrons to flow through. On the screen now is a simplified sketch of the main components of a Hull thruster. On the left-hand side of the picture and of the channel, you can see the propellant distributor ports, which are located on the positively charged anode. On the exit side of the channel, the cathode is placed outside of the channel and outside of the Hull thruster, where electrons will be drawn off of it and pulled towards the anode. Once the system is turned on, neutrally charged propellant gas will be inserted into the channel through the gas distributor ports, here seen by the red arrows, and the electrons will start to be drawn from the cathode towards the anode and into the channel, seen by the blue arrows. The red and blue bands seen represent gas and electrons flowing towards each other. As the electrons flow upstream and towards the anodes, they will eventually pass under the magnets where they will get trapped by the magnetic field here. Here they will wait for the downstream flowing gas. Upon their collision, a charged cloud of plasma is formed and subsequently ejected by the magnets, creating thrust. The plasma can be seen in orange.
Measuring the thrust of a plasma engine provides several challenges. Due to the power delivery system in the vacuum chamber, the thruster must be rigidly mounted during testing. Therefore, thrust measurements must be taken by interacting with the plasma plume exiting the engine. The plasma exiting the engine is extremely hot and electrically charged. Finally, the total thrust of the system is very low.
Now let's take a look at how we designed the test stand. The target is suspended in the plasma plume and experiences thrust through a series of collisions with ionized particles. The target is clamped to a ceramic shaft by the aluminum target grip. The shaft is made of alumina and primarily functions to amplify the force as a bending moment by creating a moment arm between the target and the load cell above it. Alumina's material properties ensure stiffness for minimal deflection, as well as thermal and electrical insulation from the charged plume below. The aluminum load cell carries extremely sensitive strain gauges in a Wheatstone bridge configuration. This allows for the measurement of strain as it correlates to the force on the target. We also designed a stress concentration into the beam which amplifies our strain by 10 times, increasing the sensitivity of our measurement system. Our load cell is fixed to the frame made of extruded aluminum members, which is suspended in the vacuum chamber. We also incorporated polymer bearings, which allow us to translate along our X and Y axis for centering our target relative to the plume.
Calibration is a vital part of this project as it provides consistency amongst testing and clarity regarding the source of measurement error. Our calibration stand is built out of 1-inch 80/20 stock and includes an adjustable height bar as well as a sliding track to hold the spring scale steady. The top of the test stand is attached to the adjustable bar with 6061 aluminum fasteners. Our calibration method uses precision spring scales to apply a load on the target disc in order to show the relationship between applied force and strain measurements. For our calibration method, the spring scales are used to apply a load to the target 1 gram at a time. At each gram increment, the voltage and microstrain readout is recorded.
Moving to a live firing of the engine in vacuum, we recorded multiple types of live data, including the temperatures of the target and of the strain gauges. The voltage across the Wheatstone bridge is recorded and turned into a microstrain value by the P3 indicator box. It is then fitted to our calibration curve to output a final force value in millinewtons. The waveform shape of the engine thrust matched our expectations, with a large initial pulse followed by a regression to steady state. While our system is responsive, the thrust values are not what we expected. The known 10 millinewton steady state force of the Busek engine resulted in a 43.5 millinewton reading from our system. Looking at the millinewton output again, the initial pulse registered at 73 millinewtons and steady state at 43.5. The 33 millinewton difference in known versus measured steady state may be a result of unaccounted for interference. We filtered for 60 Hz power line interference and used a Gauss meter to check for a magnetic field, leaving us with the plasma plume and vacuum effects. Over the coming days, we are exploring these types of interference and appropriate shielding to account for them.
This project is brought to you by the Plasma Test Stand team. Thank you.